This is my first slide. It's also going to be what I'll show next in 60 minutes or so as my last slide. So this is all I have to say. Here, what's on the slide, all the rest is commentary. And so what I want to present is a comprehensive approach to software development. Another way to describe this, actually, this is probably how I would have entitled the talk had I known in advance what Dr. Jacobson would talk about this morning. Another title for the talk might have been Method Prison. So this is what I'm going to present, another method prison. One of the pleasures of working in this area is the opportunity to disagree with Dr. Jacobson. Once in a while, we actually also agree that actually happens. On one thing that he criticized and of which I cannot be accused is fashion, because the stuff I'm going to present is highly unfashionable. It's been here for about 32 years, and no one. It's not sexy. It's actually. It has had an interesting history. For a while, it was too recent, and from one day to the next, it was old and passé. So it's one thing that it definitely is not is fashionable. So the idea is to present a comprehensive method of software development, which includes essentially all the components that are needed. And in fact, the real title of the talk, other than Method Prison, is all it takes to get better software. So you can view this as very pretentious or as somewhat modest. This kind of thing is not made for people with glasses. That's the problem. So it's somewhat pretentious if you understand it as I'm going to present to you all that it takes to produce great software. There's also another interpretation, which is to say, well, you know, to get good software, you need all of that, and we don't have it. So both interpretations are somehow correct in terms of understanding what I'm talking about. So the idea of the method is to try to address all the issues of software development, everything that it takes to get better software, and that includes reliance on a single language, and the language, of course, is Eiffel, with the ideas of seamless development, which I will explain a bit more. All of this I will explain in some detail. So I'm going very quickly through the list. Remember, this will also be the last slide, so you can basically sleep from this slide to the next instance of the slide. This is all the rest in between is distraction. Mechanisms for abstraction, concurrency, and then the second major aspect is an approach focused on quality assurance as an attitude, things should work by default, which is particularly important, and that's the part about continuous everything here, in a modern world where the difference between development and deployment and operation tends to disappear. So one of the buzzwords of the moment, but I would say a justified buzzword, is DevOps, this idea that you have a continuous cycle between development, deployment, testing, quality assurance, and so on. So, you know, if I ask you, for those of you who use Microsoft Word, if I ask you which version of Microsoft Word you are using, you can probably answer. If I ask you which version of Google Search are you answering, you can't. And it's quite possible that since the time we started this morning and up to now, there's been 10 deployments of Google Search. And this kind of continuous deployment raises the stakes in software engineering. And actually, it's extremely interesting from a software engineering viewpoint. It justifies many of the ideas that we've been promoting in software engineering. It also challenges some of the accepted ideas. But the only solution is to, I mean, if we imagine this kind of development, we cannot say we're going to develop it then we're going to test it, then we're going to release it. It just doesn't work. We need more modern paradigms. And so there's all these things about which I will talk later on, and also focus on automation. We should automate as much as possible. Yuri Brun talked this morning about automated testing. I'll have something to say about this. An important development in software engineering over the past 20 years has been the rise of empirical analysis with some successes and some failures, but what we have learned is that we cannot just accept great ideas at face value. We have to validate them. And of course, people remain absolutely key, and education. So this is going to be a hedgehog talk. And it's something a little bit scary about this, because senior people tend to, at some point, to try to get a theory of everything like Einstein, and I hope you appreciate the modesty of the comparison. And typically they fail, right? It's a very common mistake to make, but still that's what I'm trying to do. So, this is the hedgehog and the fox, like Tolstoy was a hedgehog and Dostoevsky was no, it's the other way around, or Balzac is a hedgehog and Stendhal is a fox, and so on. So the hedgehog knows one big thing. That's the background behind this book, which I hope you've read, and if you haven't, read it. The hedgehog knows one big thing, and the fox knows many little things. And in Berlin's work, this was a way to attack or to criticize the kind of French/German attitude to making complex systems of everything, Hegel style, and to advocate instead a more Anglo-Saxon, pragmatic, nothing's going to work perfectly, but by and large we get along. This was his goal, but this also describes a lot what we do in science, right? In the sense that there's a certain form of science which is fox-like, and then there are attempts at a grand theory of things, and this talk is much more in that style. I should also say that, so the source for this talk is, okay, this is not going to work. Okay. I guess this is for Herr Professor doctors who just kind of stay behind the lectern. So yeah, you probably don't know this person. He was a classmate of mine at Stanford. He did his PhD at Stanford, and he would be probably very surprised to see his picture. I found this picture on the web in this talk, and I'm sure he has completely forgotten this interaction. But it was, to me, it was absolutely critical. So in 1988, more or less at the time my book, the first edition of my book, Object-Oriented Software Construction, was published, I gave a talk at Schlumberger, where he was working in Austin, and he came to me and wanted to compliment me, and he said, I'm using your book, and of course, I'm applying the concepts to C++. And to me, this was the most absurd thing that I had ever heard. And I don't think he understood my reaction. But of course, since then, I've heard this kind of comment to me, substitute something else for C++ thousands of times, and I'm not exaggerating. And I've decided to stop, to stop accepting this, in the sense that I have absolutely nothing to say to anyone who does not use Eiffel. There's a nice weather outside, and I'm not forcing anyone to use Eiffel, but I'm not going to compromise anymore, in the sense that if you don't have the full chain, you just cannot pretend to be applying the ideas. So you don't have to agree with the ideas. There are people who prefer other approaches, functional languages or other approaches, but it makes absolutely no sense to apply the ideas without having the language support to back it, with all the components here. By the way, this approach has also been applied to teaching. We have taught something like 7,000 entering students in the initial introductory computer science introduction to programming course at ETH and now at Annapolis and so on. So coming back to the point about, the hedgehog thing, or the method prison. Most people don't work like this. That is, most people say, I have a contribution here, I have a contribution there. But we understandably stay away from proposing anything that might sound too totalitarian. And I'm absolutely not shy about being totalitarian because after all, there's no reason we shouldn't get the right answer to everything. Software engineering is very complex. It's very hard, it's challenging. We need to get everything right. So in software engineering, there's a slide which I sometimes use in my classes, which describes software engineering as a diamond without a D. So describe, implement, assess, manage, operate, and notate. These are the 6 dimensions of software engineering, with, in particular, this one, operate, becoming ever more important and hardly ever taught in university programs. When we teach software engineering, typically we stop at the production of the software, and of course, it's as in these cheap novels where the hero marries the heroine at the end, and it's the end of the story. And of course, everyone knows that in real life it's the beginning of the interesting part, and it's the same thing in software. So coming back to this list, we have these dismally disparate, distinct, and disjoint disciplines. Management, requirements, architecture, design, methodology, languages, concurrency tests, proofs, formal methods, and they're kind of handled by different communities, which sometimes talk to each other, most of the time not. And there are a few people, of course, who straddle a couple of these areas. Well, the point is that if we get one of these things, or even 3 of these things right, we're not going to get successful software projects. And we also are not going to get good sound, but that's a different problem. It's not a software problem. So why not try? Why not try? I mean, it sounds very pretentious. It sounds, to use this term again, totalitarian, but it's worthwhile trying, and that's what I want to do here. So yeah, I want to put the puzzle together. Wow. No, that's the slide. I'm going too fast. Okay. So that's the goal here. It's to use a set of compatible complementary solutions for all aspects of software developments on the management side and on the technical side. And of course, in the 45 minutes or so that I still have, I'm not going to give you everything. In this, it would take, it's not feasible, but I'm going to try to give you an idea of what I believe are the directions of success in each one of those areas. Okay, a bit of justification, which admittedly could be used by more or less any of the speakers today. I wonder why it's just me who has these. Maybe if, okay, I'll try to remember that there's an audience, because if I don't have my glasses, please, would the last person to leave tell me, because like you know, in like in Haydn's farewell symphony, the last musician, when blowing his candle, should just tell the conductor. Yeah, this is from September. So it's great stuff for professors of software engineering, right? Because whenever the press describes the state of software as being awful, it's kind of pension insurance. And so I don't mean to imply. This is somewhat sensationalistic, something like that, article. But what I found interesting actually is this, a number of things which happened on a single day in 2015, including a typo, but the typo is mine. This is the most interesting part, and I kind of hesitate to mention this in the presence of Professor Manfred Breu, who is the expert on this topic. But we used to talk about bugs in programs. This is the other way around, right? It's a bug a beetle that has a program in it, and as he may, I haven't seen his talk, but as he may tell you, the amount of software in those devices today is absolutely staggering. And sure enough, well, you can read this, right? Software now to blame for 15% of car recalls. So it's not that software has failed. That would be exaggerated. I mean, we couldn't do anything these days without software that kind of works. But the software apocalypse may or may not be coming. But we need to get our act together. And this is a bit of a digression, but this is a point that I've been hammering in blog articles to the point of making myself an absolute nuisance. But what's really scandalous in our field is that we see the headlines, they like some crash of some system, and that's all we see. We never see the explanations. I try to track these things because it's my profession, and you very seldom see something like what happened for the Ariane case, where an inquiry commission actually wrote a report, and now we all understand software engineering better thanks to this. It very seldom happens. And if you look at at airline accidents, at the airline security, which is fantastic, okay? The result over 80 or 100 years was not achieved by accident. It was achieved by accidents, okay? By having this practice, this rule of law, that every time there's a crash, there's an analysis of it. So, I'm lobbying with absolutely no success whatsoever, even though I've published this in a few places already by now, for a law which, in the appropriate countries, would actually force companies, whenever they have a serious software defect, and maybe to limit, to avoid interfering with free trade, with free commerce and so on, we have to insist that it's when there's public funding. I mean, you can put in some restrictions, but basically anytime there's something serious, there should be an inquiry commission, like in the Ariane case, so that we learn, like the airline industry has. Okay, end of digression. Now, coming back to quality, how do we achieve quality? There are a number of axes to analyze quality. One of them is a priori versus a posteriori, correctness by construction versus verification. You can think Dijkstra versus Couzeau, or I tend to think Racine versus Corneille. There's a famous cliché that every school child in France learns. Something that La Bruyère said about the two great dramatic authors of the 17th century. Racine paints people, I guess people is the politically correct term in 2017, as they are, and Corneille are as they should be. So this is like the verification people, Couzeau, or the model checking people versus correctors by construction people like Dijkstra. So and of course the answer is we need both, right? Trust and verify, or don't trust and verify. I mean build for trust and verify. Another orthogonal axis is product versus process, and it's clear that we need to get both of these aspects right. So EIFEL, which is really what I'm talking about today, in any case, it's all that I ever talk about, is about both, right? So don't think of it as being just a language, although the language is a very important component. It's an approach to software development with a focus both on product quality, correctness, robustness, security, and on process quality, in particular, with this notion of seamlessness, to which I will come back, which tries to remove semantic gaps. So it's the exact reverse of things like model-driven design, which say you're going to have a model and then you're going to have an implementation. It's trying to bring everything together. And it's based on a number of principles which are described in detail, of course, in the literature. Seamless development, close integration with the language, constructs for reliability, I'll talk a bit about these, abstraction, information hiding, open close, single choice, and so on. So certainly I'm not going to go into every one of them, but what's important here is to note that there is a theory, if you like. There is a conceptual basis which underlies any serious use of the language. So a few words about the process. One of the major advances in process was CMMI. CMMI suffers a lot, CMMI suffer a lot from the jargon and the kind of bureaucratic process of qualification and so on coming from the DoD. And as far as I know, it's not taught that much in universities, partly for good reasons, but there are some really interesting aspects in CMMI. Also, it's been a little bit lambasted by agile methods, not entirely. There have been some reconciliation between the two. This is a very interesting culture. You know, if you remove all the bureaucratic jargon and the 1,000-page documents and all the strange terminology and the acronyms and so on, there's some really interesting ideas which every software engineer should be familiar with. In particular, the idea of reproducibility of results, the idea that, yes, we should be not like the fashion industry, to repeat Ivar's points, but much more like a serious engineering discipline with reproducibility, like acoustics, audio engineering is our model. Okay, anyone still here? Emphasis on measurement, and something which is just as important, which I just forgot to include here, but it's the emphasis on self-improvement, which is also shared with some of the best agile methods. The idea of always challenging your own process, never being satisfied with what you have achieved so far. So the best known part of CMMI is the five-step hierarchy, but it's not the most interesting one. Really, the most interesting one is the collection of best practice. I mean, apart from these general principles that I just mentioned, the most interesting part of CMMI, which is somehow hampered by the name. I mean, capability, maturity, model integration. What on earth does that mean? I mean, it's not even German, and it should really have been called collection of best practices or collection of industry-approved practices. And this is the part that every software engineer or computer science student should learn, and they don't. Typically, they don't, or at least not in that fashion. Then you have the other school, the Agile Methods school. So Dr. Grün was very kind enough to mention my book, and don't worry, I'm going to advertise for my own book as well. The reason I wrote, by the way, by the way, Ivar, are you a certified Scrum Master? Who is a certified Scrum Master? Oh, quite a few, okay. But none of the speakers, haha. Okay. So, okay. And it's signed by my code, right? So, yeah. I sang the company song, I genuflected, I took the test. It's a horribly difficult test. You cannot believe how hard it is. One of the hardest parts is to pay your $100 every 2 years, which I just did, which is why this is. So anyway, the reason I wrote this book is that I got really intrigued by two things. First, the distance between what industry was doing that about 10 years ago when I started getting interested in this, which was all agile, and what was taught in universities, which had almost no mention of agile in software engineering courses. And of course, students noticed it because many students do internships in industry in the summer, and so why? Nowadays, it's not the case anymore. Nowadays, universities do teach agile. And by the way, if you know anyone who needs a good textbook advice, just ask me. I'll suggest one. The other reason I got interested in this is that when I started digging into the approach, which was largely new to me, although I'd heard about extreme programming early on from Ken Beck and others, when I started digging deeper, I was struck by the pretty incredible mix of good and bad ideas, hence the subtitle. And just as Yeah, by the way, there's a MOOC going on. It's already in its third week or so, but for anyone who is interested, you can still take it on edX. It's free, of course, and it's along the lines of the book. So to give you a kind of capsule summary of the conclusions of the book, and the good, the hype, and the ugly. So here it's in reverse order: the ugly, the indifferent, the good, and the brilliant. 4 categories. There are some really, really bad ideas, in particular things which have, I think, caused a lot of harm to the software industry over the past 10 years, the period of adoption of Agile, the dismissal of big upfront X, big upfront requirements and so on. This is an absolute catastrophe. The replacement of abstract requirements by user stories. This is a really bad idea. You get systems that perform the user stories, yeah, sure, and nothing else. So it is very simple. I mean, good systems are precisely those systems that can adapt to various scenarios. So I'm not saying user stories are a bad idea. They are a bad idea as the basic source of requirements. They are very useful as tests, as validation of requirements, but not as requirements themselves. Also, there's a lot of interesting analyses by Pamela Zay from AT&T on this in the telecom area. The use of feature-based development as opposed to abstraction or concept or based development. Some of the ideas that are fun, also good for writing papers, but not that interesting one way or the other. Pair programming. Pair programming is fantastic because it's been explored left and right. It's a fantastic source of papers because you take 2 groups of students. If your names start from A to K, use pair programming. If not, use inspection, and then we compare, and we have a paper at ICSI, maybe not at ICSI. But so there have been hundreds of studies like this, and they're very conclusive. There's no difference. Okay, it doesn't make a difference. The things that are really folklore, like planning poker, lots of fun, but completely useless. On the other hand, on the other hand, there are some really good ideas. Otherwise, of course, I would not have wasted 4 years of my life working on this, and I would not be wasting your time. There are still some people, right? The emphasis on change, the emphasis on working code, the rehabilitation of code, the rehabilitation of tests, the emphasis on constant test regression analysis. And it's interesting to see the evolution. In the original Agile books and papers, they were talking about doing integration testing and regression analysis very often, like once a week, and then it became once a day. And I guess nowadays it's more like once a minute, or maybe I'm even, this is even obsolete. No branching, okay? This is something that, yeah, branching is evil. Can you repeat with me? 1, 2, 3. Branching is evil. Good. And then there's some really great ideas, not just good, but brilliant. The closed window rule, the idea, which is not called that way in the Agile literature, but it's there, without a name. The idea that once you start a sprint, you don't add anything to it. Indeed, it doesn't matter who you are. You can be Angela Merkel or the Pope. It doesn't change anything. The list of tasks is fixed. Continuous integration. Refactoring not as a replacement for design, which is an absurd idea, but as a complement to design. Refactoring bad stuff yields bad stuff. Refactoring good design yields better design. This is very important. So, okay, this is so much about Agile just as a very brief summary. We also need a good lifecycle model. So we all love to take cheap shots or expensive shots at a waterfall, which, however, has the benefit of, first, providing a good pedagogical model on one end of the spectrum, of providing a variant, which is also very interesting, the idea of coupling every development step with a verification step. The main problem, really, with the waterfall is that it leads to impedance mismatches. Okay, if you accept, as I think we all should, that the soft part is critical in software, That is to say that the core problem, one of the core problems of software, I'm tempted to say the core problem, that's exaggerated, but certainly one of the very fundamental problems of software is the ease of change that computers give us, that software gives us, and the consequences of that possibility for change in terms of messing up our development, particularly when you couple change with size. If you have a small program, it's not such a big deal. If you have the kind of systems that we're building now, with hundreds of thousands, millions, tens of millions of lines of code or whatever the measure is, then change is an absolute spoiler. And so any approach that introduces different mindsets, different notations, different concepts at different stages of the life cycle is problematic in this respect. So, you know, you have all seen this old picture of the 1960s. It shows its age, but it's still quite accurate as a description of the limitations of the life cycle. Things like the spiral model are interesting, but they don't solve the problem either. And the main problem, in fact, with the spiral model is that you're developing successive improved prototypes. But then, of course, in industry, we all know that you don't choose when you ship, basically. Your customers do, and the competition does. And so you end up shipping the prototype. That's where, if you prototype in software, that's what happens. You end up shipping the prototype more often than not, and then it's a catastrophe. So what is needed is a model for today's world of software development where all the traditional constraints are still there, plus new ones, in particular this whole DevOps business, continuous development, integration, verification, and operation. So many years ago, in this book, Object Success, which was even available as Erfolgsschlüssel Objekttechnologie, which everyone has forgotten, of course, I emphasize this notion of seamless development. I don't want to claim that, certainly don't mean to claim that it's my idea. Already the OMT book by Rumbaugh and others talk about seamlessness, the Henderson sellers as well. But we really took this idea and made it a core part of the Eiffel approach. And the idea of seamlessness is that you try as much as possible to reduce the impedance mismatches. Of course, there are differences of focus in the successive steps of software of a project, but they are to be fought as much as possible, and instead we should emphasize the commonality of all these tasks of analysis, design, implementation, validation, verification, and so on. And this is what Eiffel is. It's the notation that, and a method that try to accompany you throughout the software development life cycle without forcing you to be Dr. Jekyll in the morning and Mr. Hyde in the afternoon, to do something for requirements, something else for design, and yet something else for implementation, and yet something else for, say, VNV. So that's the basic idea of seamlessness, this idea that we work by accretion, by addition. You know, so we start with classes, and Eiffel as a language wants to be as much a requirements description language as a design language or an implementation language, and then you have classes. So at that level, you might have classes that are closely modeled, that are very close to the model of the system that you are building, say what people call the real world, in quotes, and then you move on to design classes, implementation classes, and so on. So as an example of one of those requirements classes, and I apologize to those of you who have seen this article, this example before, because I've used it many times in public, this is the kind of thing that you could use to specify one of those vats, you know, that we have here. A vat is Fass in German, right? It's a big tank for beer or for chemicals, and so here we're describing it by saying, okay, a vat is a special case of a tank, so we're already using inheritance, and then we're using an object-oriented approach, so it's characterized by operations, by features, such as its input valve, its output valve, and an operation to fill the vat, and an operation to empty the vat, and so on. And of course, we use the full power of contracts here. We keep things deferred, meaning abstract, because we're not implementing, we're just modeling. But we can still specify them precisely. We can say, in order to fill a vat, the input valve must be open and the output valve must be closed, so that's a precondition. At the end, the input valve will now be closed, and the output valve will again be closed, and is full will be true, where the invariant tells us what we mean more precisely by is full. So you see, it's this idea of using a very powerful, simple but very powerful object-oriented notation to do everything, in particular to talk about the world. And so I tend to, after going into such an enthusiastic plea, I tend to tell my students, when you start writing love letters to your girlfriend in IFO, maybe you have listened to me a little too much. But you know, until that level, there's lots and lots of things you can do. And I have a PhD student at Innopolis in Russia who has got excited about this idea and is pushing it very far to describe in particular the requirements of embedded systems, modeling things like temporal logic and such. You can go really, really far, and there's no particular reason to use other formalism. So this is the hedgehog part, you know, the totalitarian part. And then this goes with a general model of the life cycle, which I called the cluster model in this book. It was, again, ideas of other people. I didn't invent that much, but I documented these ideas. The idea of building a system, I mean, keeping a certain sequential element, keeping a certain waterfall element, but splitting the system so that we have a mix of sequential and concurrent engineering, with, in particular, you know, extremes where you do one thing at a time, maybe for a small team, and the other extreme, which is very much like the waterfall, and the ability, the flexibility to reorganize things on the spot in real time, because we all know that projects hit problems, and sometimes it's the other way around. Sometimes some things goes faster than expected. And also a general approach, which is really fundamental in the object-oriented method, which other people have tended to forget it, which is that object-oriented development is bottom-up. It's kind of the reverse of what most Agile people tell you. They tell you to work from what the customer wants. It's often a very bad idea. Of course, you need to show the customer something, but there's a real risk that you have beautiful demos that please everyone, but then at the end you only have a Potemkin facade, because the difficult stuff, you know, the networking, the database, all the low-level clusters are what conditions the success and scalability of the system. So that's the kind of lifecycle model that we support and that we promote, and it's supported by the tools, in particular the graphical tools, which ensure a complete automatic equivalence between the textual forms in IFOL and the graphical forms. So it's like having UML diagrams, but the UML diagrams are a reflection of the text and the other way around, and they are always kept up to in sync. And yeah, I think I said this already. What's object-oriented analysis? I illustrated it in my very brief example of the VAT. It's like object-oriented programming carried out at a higher level of abstraction. In the process, an idea which I tried to develop in my book, which was based on suggestions made by someone called Roger Osmond, is, I think, as valid today as then. So the book is from '95, and the idea is totally his. I'm just the loudspeaker here. Actual loudspeaker. I should be careful when using this word. So he made a very correct point, a very convincing point to me, which is that most of the time, if you look at if you plot software development along the lines of functionality horizontally and the rest, you know, the ilities, as the previous speaker mentioned, you know, the reliability and so on. Very often the curve is kind of like the black one, because you try to add functionality and you try to make things not too bad, and then towards the end you have some hiccups. And what's really desirable is the blue line, in which you never sacrifice on quality. And the Agile people have been, I mean, some in extreme programming in particular, there is a bit of the same spirit. Whether it's applied in practice is a different matter. But for example, this idea that you don't add anything until all the regression tests pass, this is very, very healthy. It's the really kind of contribution that Agile people have made. So I think, if you think of the world of DevOps, this is absolutely critical. We cannot compromise with this kind of thing. Okay, programming language aspects. I published a blog article like a couple of years ago after this one of those software catastrophes which happened with Apple. Well, no one got killed as far as I can tell, but there was a major security breach in iPhones, iPads, and iPods due to this error here. There was a go-to that had been duplicated. Pretty basic typo, all written in C. And so I found it interesting to read this in risks. It's amazing to me. It's all those programming languages people, they're always going to claim that their programming language is the solution. That's what he was saying, right? I remember similar distractions around the Ariane 501 defect. I wonder whom he was thinking about when this person, Mr. Hamilton, wrote this. Although in that case there was nothing wrong with the code. Yeah, except that the code was wrong. But other than that, there was nothing wrong with the code. So, he's saying, the language people, they're again going to tell us that with their language, it would have been avoided. The only problem with that comment is that it's true. It's absolutely true. And why would we continue to use, for this kind of mission-critical application, a language C, which is absolutely respectable, but which was devised around 1968 to program the PDP-8, a very specific machine with very specific needs. And, I'm sorry to say, but in a language like IFOL, by which I mean IFOL actually, this kind of thing absolutely cannot happen because, because it cannot happen. I don't think I have the time to so, to me, those who say language, it's a very common observation. Programming languages, don't bother us with programming languages. Quality that counts, it's process that counts, it's whatever else that counts. So to me, those who say that languages do not matter are just there to defend bad languages. That's the only purpose. So as an example of the kind of things that we do, you can always say, okay, IFOL, why not Java, why not C#, why not Python, and so on. Well, if we take object-oriented languages in particular, there's this absolute plague of null pointer dereferencing. Even Tony Hoare says that it's his billion-dollar mistake, which is an exaggeration in two ways. First, I think it's much more than $1 billion, and second, it's not just his mistake. But still, we have someone quite famous telling us that it's important. And so here's an example. So what's a null pointer dereferencing? In all object-oriented languages, you can write x.r, possibly with arguments, meaning apply r to the object to which x points. Except that x is a pointer, or you can call it a reference, but it's the same thing, and it might be void, null. No, void is the Eiffel term, it's more commonly called null, and then boom. Okay, little detail, and since the start of this talk, I'm sure that quite a few, maybe not billion, but millions or let's say hundreds of thousands of dollars have been lost because of some Java or C++ or C program, because this also happens in C, crashing because of this. So for example, we all know the JPEG standard. Well, if you use JPEG, this is 1 year ago, from the CVE Common Vulnerabilities and Exposure database. So in JPEG, they found a null pointer dereference, which gives a security attack. And my student, Alexander Kaktenkov, who finished his PhD thesis not very long ago at ETH, looked in the archives of CVE, which is the main repository of security attacks, and this is what he found. Like about 70 a year of the major security attacks recorded by CERT or by CVE involve a null pointer dereference, maybe along with something else, buffer overflow, whatever. So this is serious stuff, right? And in every single commercially available or production quality object-oriented language available, it can happen. So we spent many years and lost quite a few quite a lot of hair getting rid of this in Eiffel, following the lead of some research languages, in particular some C Omega at Microsoft Research, and we completely got rid of it. So, when you have this in Eiffel today, you have the guarantee that if the compiler, it's like type checking. If the compiler accepts it, then it will not produce a null pointer dereferencing, and basically Kaltnikof's thesis proves it using various proof tools. So to me, this makes a major, it's the kind of thing that makes a major difference. So I'm not going to describe the components of the solution. What's really interesting is that coming up with a basic mechanism took about a half day, maybe 2 or 3 days. Engineering it took 10 years. It's finished now, at least we hope so. And this is because the problem is not to disallow null pointers or null pointer dereferencing. That's very easy, just reject every program. Okay? So the problem is to have a realistic mechanism that still enables people to write reasonable programs in a simple way. So it took 10 years, but now it's okay. Another area where Eiffel makes a real difference, in my opinion, is concurrency. The US Academy of Sciences produced a report a few years ago talking about parallelism. I think they were focused more on high-performance computing, but it's still quite true of concurrency in general. And the interesting thing here is to talk about heroic programmers, right? We all remember, at least those of us who have been around for a while, we all remember when it took a hero to produce any kind of significant program. And a major advance of the field over the past 40 years is that you can produce a reasonable program without being a hero. This room accepted, of course, I know you are all heroes. But other people who are not as heroic as you are can produce programs. And in the area of concurrent programming, you still have to be a hero. This is a standard algorithm for the famous Dunning Philosophers program. And in order to understand it, you have to do what Dijkstra criticized very aptly in his go-to paper, talking about the conceptual gap that exists between the program text, which is static, and the dynamic process, which exists in time. So this is what, if you want to understand this, you have to turn yourself into a computer. Like with a go-to, like for a program is a go-to. You have to reason completely operationally. And if you write the same thing in Eiffel, did I miss it? I think I mistakenly removed the slide. This is the danger of fiddling with your slide at the last moment. But the equivalent in Eiffel, in Scoop, which is the Eiffel's mechanism, is crystal clear and a few lines of code, which anyone can understand right away. Here's another example. I mean, what's hard about concurrency? The problem with concurrency is that we can no longer apply the basic scheme of relying on abstraction. And if I see something like this, a transfer operation between accounts with a certain precondition which says there has to be enough money on the account, on the source account, and a post condition which says, well, the money will have been transferred, I don't need to see the implementation. I can reason on the basis of the API. But the problem, of course, is that if we are now in a concurrent context, then all bets are off. All our old assumptions go away. And in fact, the whole business... So this is programming concurrent applications without scope. The whole edifice of civilization falls on you as the temple on Samson and Delilah at the end of the Saint-Saëns opera. So that's what Scoop is about. It's simple. I mean, the S is for simple. And to me, it completely changes this issue of concurrent programming, which ceases to be a completely scary aspect of programs, as it is with, for example, the standard thread libraries, which is what people use to do concurrency, Java threads and the equivalent. It's completely different, and it does for concurrent programming what I think structured programming and then object-oriented programming did for sequential programming. Okay, design by contract. I think I'm not going to bore you with the details, except to indicate what happens when people do not respect.
A final decision to go was taken.
10, 9, 8, 7, 6, 5, 4, 3, 2, unité, feu.
So here you have to understand French. He's saying all the parameters are according to expectations. Listen to the comment.
Tous les paramètres propulsifs sont
Tous les
normaux,
paramètres sont
trajectoire normale.
all the parameters are normal. Well, not
37
quite.
seconds into the launch.
So with my colleague Jean-Marc Jessekel, I wrote an analysis of this, which is not so much to boast of in the sense that the real work was done by Alain Deutsch from INRIA and Gilles Kahn and people. So we interpreted their report, but still, anyone who claims that this is not a matter of programming or not a matter of programming languages really doesn't know what he is talking about. Another aspect of contracts which is less well known because people always think about the effects on verification is the consequence on documentation. You know, the contracts are really the only way I know to document APIs, for example, seriously. The danger otherwise is to have what I call the French driver's license syndrome, which is illustrated here actually on the left and on the right? So if there's anything almost as bad as no documentation, it's bad it's documentation that is out of sync with what it documents. So this is my driver's license. So once a French driver, always a French driver. Right? It's not like in the US. You don't have to renew your driver's license all the time. So this is actually my French driver's license, and you can see the specification on the left, and you can see the current state of the implementation on the right. And this is the description of many a program and its documentation. And so having this technique of extracting the specification, extracting the documentation from the code goes a long way towards alleviating this. So to finish, because indeed I promised I would finish eventually, I would like to describe some of the things that we did in recent years. It's kind of, unfortunately, it's kind of stalled at the moment. I really hope to be able to restart these projects in an industrial context because there's nothing to be done in Europe in academia anyway. I think that's pretty clear to everyone, but here's what we are able to do. So, and this relates a bit to some of what Professor Brun mentioned this morning. If you talk about test automation, what can we automate? Okay? The easy stuff has been done. And by saying easy stuff, I really don't want to downplay it because it was very important. Tools like JUnit, XUnit in general revolutionized the field of testing, but still, it's the easy part because it's automating the execution of tests. What we really want to automate is test case generation and oracles. He mentioned oracles this morning. So for oracles, using iFool, we are in good shape because we have the contracts in the code, right? So you just push the button, you go to lunch, and you wait for a post condition to fail. That's the idea. And the test generation, there's ample, we've published a lot on this. It's called auto test. It uses techniques that sound stupid, well, silly, but maybe not stupid, but silly, and which work really well in practice. For example, we found a considerable amount of errors, of faults in software that had actually been used extensively. And also one thing that found, I mean, many people told us they were not surprised, but still to me it was very interesting. So we have this automated testing. And what the what the narrow line shows is branch coverage, which in many cases reaches close to 100% very quickly. It's completely automated, right? Test cases generated automatically on object-oriented software. And this is the thick line is, like here, for example, it's bugs found by autotest. And so what we see, and we reproduce it on many different classes, many different examples, is that if you're shipping with, at a certain level of branch coverage, you might be shipping, here. 90%, or in this case, almost 100% branch coverage. Great. I mean, it's much more than what most of industry does. I don't know what your criterion is, but many people say at 80% I ship. And I know many companies that use a much lower threshold. And you can see that it continues finding bugs. So this is something that we learned. Everyone else told us that they knew, sure. And the last, so there was also a tool that I find very exciting, which used this information to actually fix programs. And the test of this kind of thing is reality. So we have the benefit of working with a real software base, Eiffel Studio, and in particular the Eiffel-based library, which have been developed over something like 30 years, but they have really been in a repository and followed, well recorded for about 20 years. So we can mine this. And we found that in many cases, the fixing tool, surprise, surprise, for bugs that existed and were fixed at some point, suggests the fix that the programmer applied in reality or something very close to it. The last thing I would like to talk about is proofs. So the other part of this tool battery is autoproof, which potentially, it's not a commercial product, it's really a research prototype still, but potentially it would compete with things like Spark or B, which are, to me, the reference, the state of the art in this field. They are very interesting tools, but mostly they force you to renounce much of what makes life pleasurable. I mean, would you really want to go to work in the morning if you knew that you cannot use dynamic allocation, classes, objects, inheritance, single and multiple, polymorphism, dynamic binding, generics, and so on? I would not. I mean, I would stay in bed, personally. And so this is what you have to do. You have to take monastic orders, so to speak, in order to get your software verified, and that we refuse. So what we do with autoproof is that we take a full-fledged object-oriented language, Eiffel, and we do proofs. And let me, as the last thing, if the organizers will let me give you an example of autoproof. So it's all on the web. You can do it, and I've done this demo in public in the past. I apologize. I mean, if anyone has seen it, just don't say anything when I run the quiz. So this is very similar to the bank account class that I showed, and I'm going to run the verifier. So when I click run here, it's very misleading. It doesn't run the program; it runs the verifier. So nothing gets executed, right? Except maybe the PhD student. But other than that, there's no execution, right? It runs the verifier. Internally, I should have said it, internally it relies on the work of many people. It relies on Boogie by Ruston Leno and others from Microsoft Research, which itself relies on the Z3 SMT solver. This is the autoproof technology stack. And the biggest thing that we did with it in the PhD thesis of Nadia Polikarpova was the full verification, full functional correctness proof of the Eiffel-based 2 library, which is a kind of Java collections, if you like, the equivalent of Java or C# collections. So Knusware, stacks, queues, lists, and so on. So here it's simpler. So let me run the verification. So you can see that the class has balance, has deposit, it has withdraw. So let me run the verification. I hope the connection, yeah. And so it cannot verify withdraw. Can you see the font, or should I make it bigger? At least those who are reasonable. So who cannot see the font? Or maybe it's because they cannot hear me anyway. So who can hear me and not see the font? Oh, okay, so sight and sound are okay. So here, since we're running out of time, you can see, I hope you can see the mistake, which is a plus instead of a minus. That was easy. Okay, so now the next and last one is going to be a bit more subtle. So you can see that it cannot verify. Verify means proof, right? It's real proofs, not tests, no execution, once again. The post condition may be violated. So what is the post condition? How do I show enough of this? Sorry, yeah. This is transfer. And the post condition that is not satisfied is balance decreased. Actually, don't tell anyone, but as a cheat sheet, the other post condition also doesn't verify, but it stops at the first one. It's not a very sophisticated UI. And so the post condition says balance equals all balance minus amount. And what does the code do? It does what a reasonable self-respective transfer operation does. It withdraws from itself, and then it adds the same amount to the other. So, okay, no break until someone says what's wrong here. Someone who has not seen this before, okay, not cheating. Well, yeah, but okay, I shouldn't do this with Professor Boy in the audience. Okay. He wants to have, you want to have your coffee break, I know. Yeah, so if I add the condition that other not equal to current is the current object, right? This in Java, then it verifies. And so to me, this is very interesting in terms of where the state of the art is. This particular example is interesting because it's typically the kind of relatively subtle bug that will actually happen. Why would a programmer think of transferring some stupid user transferring from an account to itself? And of course, there's no reason to transfer from an account to itself, except that after 2 months of smooth, successful operation, the variables are going to be such in one execution that the whole thing will crash, or worse, produce incorrect results. The stakeholders will be, the shareholders will start screaming. Something bad is really going to happen because of this extreme case that no one had thought about. And this is typically the kind of thing that human testers don't necessarily think about. Automatic test might find it, but of course, proofs are even better. And this is the state of the art today. I'm really eager to restart the development on autoproof. I think it's close to, it requires, I would say, I don't know, €500,000, maybe €1 million, so a year, 2 or 3 person years to really turn it into a practical tool that people can use on a day-to-day development. It's not that far. So that's what I've presented, a comprehensive, or bits and pieces in a somewhat impressionistic fashion of an approach to software development that tries to include everything, or at least to have answers to everything. It's too easy to say, okay, I'm focusing on this and I let other people take care of the rest. It's normal, of course, this is how you do research, but if you want to be a bit more ambitious than that, you cannot forever ignore the rest, especially since you tend to ignore the stuff that bothers you, that you don't have answers for. So here, we're trying to develop an approach that will actually have something to say about everything that is significant in software development. And, in the end, there's nothing wrong with being consistent.